Okay, hi, we are in chapter 15, which is the impulse and momentum. So here we have a pile that is embedded in sand, soft sand, and then we have a hammer that actually the hammer is tied somewhere, right? So it's at rest, and that cord, let me put it actually straight, is subjected, so it's at rest at the beginning. So right here is at rest, and it's let it fall, right? So it will hammer, it will hit the pile, and it says that since there is a sound, it sticks together, so it doesn't rebound. And they want us to find what is the impulse exerted from the pile to the hammer, which is the same impulse exerted by the hammer to the pile. So this is a several-step problem. So the first thing that we have to find is the velocity in which the hammer hits the pile. To do that, so let's call it step 1. We will do conservation of energy. Between this position, we can call this position 0, and this position 1, between 1 and 0, right? So as you recall, to do the conservation of energy, we use the principle of work and energy, in which case work of non-conservative forces is equals to, in this case, I'm going to use T1 plus V1 minus T0 plus V0, so it's a 2 position, and that will be from position 0 to 1. But since there is no non-conservative forces, because the only force that is in the system when I cut that string is the weight of the hammer, and the weight can be considered conservative forces, so this is equals to 0. Therefore, there is conservation of energy, right? T1 plus V1 equals to T0 plus V0. And so we said that at position 0, the hammer is at rest. So we have no kinetic energy at position 0. And what do we have if potential energy? If we put our datum right here, we have no potential energy either. For kinetic energy in position 1, we will have 1/2 mass than velocity of the hammer, right, in 1 square. And since I put the datum right here, I lost potential energy. So I will lose mg at that h, and that h is 0.5, right? And that's equals to 0. As you see, mass cancel out, and from here I can find the initial velocity of the hammer, which is equals square root of 2g 0.5. And this is the square root of g, because this one goes, that's 1/2 times 2, right? So from here I can find that the initial velocity before the strike is equals to, and I have it right here, 3.13 meters per second. So this is the first velocity. This is the velocity before impact. And then let's go position 2 right after the impact. So now we are going to analyze the impact. So step 2, analysis of impact. And this is before impact is 1, and after impact is 2. For that, we will use the principle of impulse and momentum. We will do first our diagram of impact. And since they say it doesn't rebound, I will put the pile and the hammer together. So I will do my hammer and the pile together in my... And what forces do I have in my diagram of impact? Remember that forces like weight are very small in compared to the impact that is occurring there, so we can neglect weight, and we can neglect the force of the normal force, because since it's sand, it acts like as a spring, so we don't have any force. And the forces that are internal, which is the impact forces, are cancel out and are considered internal forces. So as you see here, if we do our principle of impulse and momentums, then we know that this is the linear momentum. After the impact, we call them 2, right? And this is the mass minus the, this is each of them, and linear momentum before the impact. So this is after the impact, we can call it 2, and this is before the impact. So is the difference in linear momentum? We know that this is 0 because as we analyze our diagram of impact, we don't have any impact. So we can say that there is a conservation. Let me write it here. Conservation of linear momentum. So we know that before the impact and after the impact is conservation of linear momentum. And what is it? So before the impact, this is at rest. So the pile is at rest before the impact, and the hammer, we already calculated the velocity that has right before the impact. So, and this is what we want to find. And since it doesn't rebound, they move together. So we can say that at the end, the mass of the hammer plus the mass of the pile times the final velocity will be equals to the mass of the hammer, velocity of the hammer, plus the mass of the pile, velocity of the pile. But we know that the pile is at rest in the position 1. So from here, we already found the velocity of the hammer, so we can send the velocity 2 will be equals to the mass of the hammer, which is 300 kilograms, times the velocity that I already found, over the total mass, which is 300, plus 800. So from here we can find the total velocity. This is the velocity of hammer and pile together. They move together because the hammer doesn't rebound. And that's equals to 0.8542 meters over second. Now, they want us to find the impulse the piles here. So we need to find that internal force that we don't see here. So step 3 is do the impact diagram of one of them, because as you see, if we do the hammer or we do the pile, the internal force that one produces to the other one only entails impulse. So this is the reaction force, or the reaction impulse actually, and this is the reaction impulse. That's why here we didn't see them. And here they cancel out, but we will take that into consideration only. So if we rewrite the principle of impulse and momentum, right? So let's do it for this free body diagram, or this. I like to call it impact diagram, right? Because it's different from a free body diagram in the sense that I am neglecting the weight and all the forces that have a finite magnitude. And that will be equal, since I am doing only, I'm taking into consideration only this free body diagram, I'm going to say that is the mass of the hammer, velocity 2 of the hammer, minus mass of the hammer, velocity 1 of the hammer. And that will be that reaction that I'm looking for. Therefore, reaction that I'm looking for will be equals to the mass of the hammer, which is 300, times the velocity 2, which is fine. We have to be careful with the sign, because here we will get negative sign in the sense that we are naming this as a positive, right? This is our velocity. So if this is a velocity, you will see that our force have to go in the opposite direction of the motion. So this is the velocity, 2 minus 300, and the first velocity was 3.3 meters, right? Therefore, our R is equals to negative 683.4. What it means is that it goes up because I named my velocities positive to go down. So the units are not only newtons, are newtons per second because this is an impulse. And that negative means that it goes up as I draw it right here. So I could actually have said, well, okay, if all my positives are down, so my coordinate system is this is positive, then this is negative, and then I would have gotten positive values, right? Okay? The important thing is that we know that the velocity goes down and the reaction force goes up. So we were able to find the impulse that the pilot hurts to the hammer, but in order to find the impulse, we had to find the final velocity in position 2, and in order to find the final velocity, we had to find the initial velocity before the impact.